Our first panel of the day is representatives from Helicity Space. Those of you who were in Tucson 2 years ago saw some of their material. They've made a lot of progress. I would introduce to my right, your left, Stefan Lindner. Stefan is co-founder and board member at Helicity. He's currently CEO and co-founder of GECO Bank. Prior to founding GECO and Helicity, he worked as an MD at Goldman Sachs Security Divisions, 15 years experience in finance and capital markets. Caltech PhD, that's all right. And applied computational mathematics, degrees in machine learning, computer science from a university in France whose name I'm not going to pronounce. So, Stefan, glad that you're here. In the middle is Set Yu, chief scientist and co-founder of Helicity Space Corporation. Dr. Yu's area of specialization is experimental and theoretical plasma physics applied to fusion energy, space propulsion, and astrophysics. PhD in physics from Imperial College London. Obviously, this is a very undereducated panel we have here. Imperial College London, he was at the Cullum Center for Fusion Energy in Japan at the University of Tokyo, and also at Caltech and U Washington with the support of the UK Engineering and Physical Sciences Research Council, the Japan Society for the Promotion of Science, and an early career award from the U.S. Department of Energy. Wow. And then we have Alan Stern. And the notes that I got from Andrew said, well, Alan needs no introduction. So I have no notes on Alan, but I've known Alan for many years since I was at Georgia Tech. Alan, I think everybody knows, is been PI on the New Horizons mission to Pluto. He works at Southwest Research Institute. You are on the board of Worldview. You're on the board of Moon Express. What other things am I forgetting that you need to talk? We kick this off, and I'm going to sit down and let you have the panel. Thanks for being here, folks.
Yeah. Thank you, Stephen. Thank you, Stephen, for getting us going. We are your post-lunch entertainment, and if we catch you falling asleep, we're going to call you out. So don't do that. Okay. So we have an hour, and if I can get the next slide, let me just tell you a little bit about the run of show, if I can. So Helicity is a small tech development company based in Southern California. In fact, not very far from the Caltech campus in Pasadena. And what Helicity is doing is developing a practical fusion drive to change the game of in-space transportation. And you have here, as you already heard, the company's chief scientist and the company's CEO and co-founder. I am a advisor to the company. I'm a working planetary scientist. I've been involved now in 29 NASA and European Space Agency missions, half of which I was principal investigator for. I am a member of the U.S. National Science Board, the former board chairman of the Commercial Spaceflight Federation, which is the industry association in the United States for the whole commercial spaceflight industry, and the former head of all NASA science, all the science missions from the Hubble to the rovers to the Earth Science and all of the grant and research programs that went with it, about a third of NASA. And I came to work to help Helicity make this dream come true just about 2 years ago. And what you will see is that this is not a ViewGraph company. This is a company that's actually building and developing the technology, first in ground-based and then moving very quickly to space-based demonstrations that will take us to successive levels of maturity to develop actual fusion drive propulsion for practical purposes in the 2030s and across the rest of the century. So as I said, the run of show is that Set will very shortly say a little bit more about himself and his role, and then Stefan will do the same thing. And then Stefan is going to make the first of 3 presentations. Set will make the second one, more focused on technology. Then I'll talk a little bit about the applications. If we have time, we have a couple of preset questions that we want to make sure we cover. But if we don't have time, we want to give you time to ask questions about what we're doing and what's exciting us about the distant future. So I think with no further ado, Set, can you say a little about your role?
Thank you, Alan. So I'm just a geek in the company. And I've been wanting to do fusion space propulsion forever, ever since I was a kid. And I learned about flying in space and wanting to become an astronaut and fly. I spent my whole career learning how to do fusion. And there's many, many different ways of doing fusion. And I tried to find a scheme, a method to do fusion that would be appropriate for fusion propulsion primarily as a goal. So that was the idea that helped start the company. It's really trying to identify the most pragmatic way to do fusion. And basically you can think of it as how small can you make a fusion engine? That's really the answer we're trying to answer right now.
Thank you, Seth. So I'm Stefan. I'm the, like Alan said, currently serve as the CEO. I have a full-time job on the side. My background was in mathematics. I was an applied mathematician at Caltech, and applied math means you apply them. I ended up applying them in finance. So I went to the dark side and which in retrospect has been really helpful, because otherwise a company needs funding, and being able to raise capital is also useful especially for something like this. A fusion drive isn't exactly yet a commercial application. So getting that all together, it's a little bit the magic that we're doing all together here or trying to present here is an actual company, like Alan said. And well, with that, I think we can get started. So I'll be talking about the company for a little bit. The technologies set will really describe that, and I think that's the part that this audience will be particularly excited about, as well as Alan's presentation on the applications for interstellar. This is not news to anyone in this audience. I can go fast on those slides, but you'd be surprised when we pitch. Most people don't necessarily understand that with chemical propulsion. You can go to the next slide. You can only go so far or so fast. Our goal is to try to solve that with fusion, particularly for interplanetary travel. That's where it's most useful. Interstellar has real applications as well. If you've seen the show Away, we all know how painful it would be to try to get to Mars with chemical propulsion. So the company is here to try to develop propulsion systems. We're not really in the business of trying to solve fusion for terrestrial purposes. There's a lot of other companies with lots of funding that's flown into the fields. We look at this as a very different problematic. Our goal is to push a spaceship forward. It's not to power New York City sustainably for a while. It's a very different problem. Net gains and everything else. I'll let Seth describe that more. We're here for propulsion because, like Seth says, that was his passion. I grew up reading Asimov and all the good stuff as well. We all want to see this happen. So no mystery. No mystery for this audience. Fusion is the answer. I don't think anyone here needs an explanation on that. We're aiming for the high quadrant there on the right, high power, efficient fuel consumption. And we've known that since the 60s. The interesting part, commercially especially, is that there's been so much progress in the field over the last 40 years. We don't have fusion on the grid. And in fact, I'd like to be a little humble. We all know that there's not a single company fusion driven that has yet produced even net gain. So the field is mature, but it's not yet to the point where anyone is freely producing energy. There's lots of claims where part of what we're trying to establish today is that this company is serious. We're going in steps. We have a breakthrough. We think we can go far, but still we have a lot to show, and we know that. So fusion is a hard field, and I just want to acknowledge that. So this is the dream, okay? The technology, you see it here. Again, Seth will describe it in more details. You see these jets. There's a bunch of them. Part of what you want to remember is the more jets, the more power these fusion drives get. That makes them scalable. You can make smaller underquote versions. They're still nothing here is handheld. We're talking physics fusion, so there's still a certain size. But the more jets you put, the more power you get. That means from a product standpoint, you may have applications before humans need to fly to Alpha Centauri. Maybe we can take probes to Mars faster, and we have incremental technology. That's, from a commercial standpoint, what's so exciting about this. Again, I'll let Seth explain the actual technology, but the promise is high power. This is clean, doesn't require radioactive fuel. It's agile. You can go the Mars. The quote we like to give is, for the larger missions, 450 tons to Mars, a round trip in 4 months. We insist on round trip because that means you can go anytime, you come back anytime, you don't have to wait for orbits to line up. And the reusability, of course, being very important. The company itself, it was formed in 2018, so a little while ago. But like all hard deep tech companies, we spend a lot of time first making sure that we were fundable, and we had a technical roadmap that made sense before raising money for hardware. Hardware is expensive, as we all know. So the company was formed just fresh on the back of the discovery of the plectronemic jets that Seth will present. A lot of time was spent first talking to NASA, talking to DoD, meeting amazing people like Alan and some of our other advisors, Pete Warden, Bill Reedy, and others, to make sure that we had a shot, not just technologically, but also commercially, and dotting all the I's, crossing all the T's. And finally, in 2021, we got real capital to start a lab. The team's been executing like a clockwork. In Pasadena, there's real things to be shown. Seth will give you some videos. We're not far from some very interesting results, and we're always open to investors. and this is the team, the founding team. We have Marta in the back. She runs our operation. She's under the panel, and Jeff, one of our board members and early investors as well. So this is the team that's currently operating the company. Some of our advisors are listed on the next slide. You may recognize some faces. One highlighted in yellow right next to me, but also Bill Reedy, former NASA administrator and commander of the space shuttle. Pete Warden, who also needs no introduction. Ty McCoy on the DoD side. We've been actively working on getting known in the right circles, getting ready for funding at the right times. We still have a lot to show. We also have a scientific advisory board that's worth highlighting. A number of plasma physicists, notably Dr. Paul Ballin at Caltech, and we're still actively collaborating with them. That's part of why we put the lab back to our alma mater, for Seth to be able to work directly with campus. Now, if you think of the company's roadmap overall, again, there's technically, I'll let Seth describe more the technical roadmap, but overall, you want to think of it as having two streams. One is the fusion stream. Small devices, make it bigger, get the fusion neutrons by 2026, 27. Our goal is to have a proto-flight in space in 2032. So that's 9 years. That sounds far. If you're an investor, it sounds pretty close. If you have to develop it all, we're trying to balance those two competing forces realistically. So we have milestones behind. We're trying to go at this in steps. Part of it on the side is to try to harden things for space. So while, of course, the primary focus is to get the concept to get some fusion on Earth as soon as possible, we also need to harden everything is about space flight. So getting the masses down, getting all the different subsystems and all that. So we have some plans for flying a first plectronemic jet, if all goes well, in 2026. The technological roadmap long term, if you think of it, if we get to a proto flight in the early 30s, what you'll get after that is what you see here in the middle, what we call the fusion augmented solar electric propulsion. You've got solar panels, you load up capacitors, you fire, and you get a pulse, a pulse that has freed up a little bit of nuclear fusion energy in the process. That is not self-sustaining. It's not yet a full reactor, but you get more power in than you collected from the solar panels. And that, while that won't take humans to Mars, it can take larger rovers. It has lots of applications already for NASA and for exploration, for DoD. So we have an incremental roadmap, which for the company is so exciting because we don't have to wait till humans are flying to Mars to have a product to sell. This has incremental abilities. And again, I'll let Seth describe that further. Expanding capabilities, mostly for Alan to pick up at the end, but visually you want to think all the way from cislunar military applications to bringing telescopes to interstellar missions and looking at solar gravitational lens, etc. So the dream is there. Again, this audience does not need to be sold on it, but we're hoping to get there. The last slide, and then I'll be done on my side. This is an American company. We're raising European and American capital. It does have, what we do has national interests strategically. We don't want to be too naive about that. ITAR and everything else. This technology needs to be developed, and we'd rather have it be in the hands of the free world. And we're doing everything we can to keep it there. And with this, we'll go to the interesting part, which is the technology.
Thanks, Stefan. So if you want to remember one slide, you probably want to remember this one. This is what summarizes the concept. It's a pulsed magneto-inertial fusion system. Some people know it as a magnetized target fusion, but it's primarily developed from the ground up with space propulsion in mind first. It exploits three key physics discoveries that we've had in the lab. So I'll describe those in detail. Number one is the confinement method, which is a magnetic confinement method. A preheating method, we use magnetic reconnection. And then we compress as well the plasma using magnetic fields to raise the energy density. So the paper there is a direct link for those that are interested in reading the physics behind it. The main result really is that the fusion triple product, the product of density times temperature times the confinement time, scales with the number of plasma sources. That's a new factor in the triple product equation. It still has the same factors as the conventional triple product equation: current, the compression ratio, the magnetic field strength, the plasma size, and things like that. But the fact that we have that n raised to the 3/2 means that we can compensate. We have an extra control knob, if you want, on trying to improve this triple product in the lab by increasing the number of plasma sources. And that's what that illustration is supposed to show. We have like 20 plasma sources. So it's a bit like a car engine. Instead of trying to increase the power of a fusion engine by just increasing the size of the machine with one plasma source, you distribute it over a lot of guns. That brings some engineering advantages. You can compensate for uncertainties in the confinement time just by increasing n. And then you can start testing the idea much earlier on and then keep on going. So the first thing is, how does it compare to all the other fusion propulsion concepts that have existed in history? So this graph shows the specific thrust power, the amount of thrust that you get out per unit mass as a function of the plasma density. So plasma confinement methods go from low density on the left to very high density, much more than solid density on the right, and magnetized target fusion somewhere in the middle. The size of the circles roughly represents the mass of a certain engine. And on the left side, at very low density, steady state magnetic confinement is pretty big, pretty heavy. And then on the right, the inertial confinement fusion ones are huge, and they need very high pulse rates to get those kind of specific thrust powers. The magnetized target fusion in the middle, intermediate densities, seem to be a bit more compact. And the difference between ours and other magnetized target fusion is that we're a little bit more efficient and smaller, with more modest pulse rates. And, when we're interested in fast travel, we need really good thrust per unit mass. For fast interplanetary travel, anywhere between 1 and 10 kilowatts of thrust per kilogram, and then 10 and above for starting to go to the Oort cloud and beyond. So I just want to give you a primer as to why we chose a specific method. Why didn't we just go build a tokamak or something like that? And to do that, I'll give you a primer on how to achieve fusion. The two conventional ways is magnetic confinement on the left and inertial confinement on the right. With magnetic confinement, you take a magnetic field and you hold the plasma in steady state. It's usually low density because it's limited by the strength of the fields you can create. And then you have to find some way of heating it, a steady state heating to 100 million degrees. On the right side, with inertial confinement, you forget about steady state. So you make a solid pellet of fuel, deuterium, tritium, or deuterium, deuterium. And then you just crush it with lasers, basically like Thor's hammer, and you crush it completely to 100 million degrees before it breaks up. You have to do that in nanoseconds. In the magnetoinertial confinement state, you take a plasma that's held to medium amount of density with slightly strong magnetic fields. So it's not there for very long. It loses heat reasonably rapidly. But then you try and compress it on that medium timescale. So the advantage is normally you're supposed to have more compact machines because you are higher density compared to magnetic confinement. And you have more compact compression drivers compared to the laser inertial fusion ones because you don't have to have a very, very fast timescale. So it's an intermediate Goldilocks zone. And that's our class of fusion. Now, how do we confine our plasma? We confine them with these things that we call magnetic plectonemes. They're Taylor states for those that are interested in the details of the magnetic confinement method. It's related to things called spheromags, which are Taylor states. And you can think of it as a donut that was stretched and then twisted and stuffed inside a cylinder. You can do that very naturally with your rubber band. And we've discovered those in the laboratory quite by accident. but it was predicted theoretically 40 years ago. 40 years ago, they were studying the stability of these magnetic donuts, these spheromags, that would be naturally tilt unstable. So it would kind of tilt, and then because it would tilt, people would say, oh, it will die at that point, and then you would not be able to confine the plasma, and therefore it was useless as a fusion reactor. But people have been studying this in the late 2000s and suddenly realized that the plasma did not die. It actually reconfigured itself from a donut into this double helix plectronemic shape. What we've done in this experiment called MOCHI is discovered it occurred completely spontaneously and naturally inside a very stable, long, 1 meter long plasma jet. That plasma jet is stabilized through helical shear flows to the conventional kink and sausage instabilities, and the magnetic field inside is extremely well confined. So I can show you the movie as to what the jet looks like. This is a meter-long jet taken with a high-speed camera. It lasts about 100 microseconds in this case, developing these straight twisted magnetic fields. So the second physics phenomenon that we were exploiting is something called magnetic reconnection. When you take two objects that are confined inside this magnetic field and you smash them together, they merge into a single one. And then the magnetic field that is dissipated during the reconnection is transformed into ion heating, internally, extremely fast and very, very efficiently. We've done that, so the graph on the right-hand side shows the worldwide database of this what we call merging reconnection of various donuts, tokamaks, spheromags, as well as a plectroneme. So on the bottom left, you see an experiment that has produced two of these double helix objects and smashed them together and observed a rise in temperature, a delta T, from about 10 to 100 eV. So it was extremely efficient, extremely fast. So the goal of our company is to exploit this, but not just with two objects, but with an n number of objects, and then go up at high density, so we're on the high density curve, and then go up the temperature, basically, in that sense. So then the third aspect is to compress the whole thing. So once you've merged it and preheated the plasma, you will be able to then compress it. Now, it's a conventional magnetic nozzle type geometry with copper coils. So it's conventional coils. We don't need superconductors. And then we just arrange it in a kind of a reasonably efficient method, which we call a constant energy compression or peristaltic compression method, where we send double pulse current through this transmission line, and it transforms the current into magnetic field at higher density as the radius decreases. It's a little bit more efficient than having just solid coils at a given radius and then increasing the field and trying to compress it because you create more field lines that way. Combining all three gives you this 4-stroke engine. So the 4 strokes are effective. First, you form a large number of these plectronemic jets. You shoot them into this double pulse magnetic field. They merge together in the center, are preheated, and they literally just preheat the ions only. So it's internal, high power, and very efficient. No one else does this. And then you compress it to be able to reach this thermonuclear regime. The reason you preheat it is for multiple reasons. One, you reduce magnetic compression ratios. Magnetic compression is a very old idea. People have demonstrated in the lab how to compress a plasma to higher temperature. They compressed it by maybe a radius a factor of 3, volume a factor of 10, which effectively increased the temperature and density adiabatic. So it works. The problem is you're not very efficient. You need to increase it by a factor of 1,000 to be able to go from 10 eV to 10 keV. So if you preheat the plasma to say 100 eV, you only need to increase by a factor of 10 to get to 1 keV and a factor of 100 to get to 10 keV. The other thing is because we use magnetic reconnection, we preheat the ions. That's very good for fusion because ultimately fusion is a fusion of ions and electrons are just a loss of energy. They just radiate energy away. So by internally heating the ions very rapidly, you have a non-isothermal temperature between the ions and the electrons. So now the compression doesn't have to be done on the short timescale of the heat loss of electrons. That's really, really fast. Electrons tend to lose energy very quickly. But you can compress on the ion timescale. So it reduces the compression challenges, which means that it's a bit more practical and feasible. Now, once you have fusion, you have a very high pressure but low density or medium density plasma. Then you want to augment the thrust and then bring down the ISP from the fusion temperatures to a cooler temperature for your flight profile, depending on your desired ISP at point in the trajectory. So then you would mix it with a cooler propellant where no fusion reactions happen. You just cool the whole thing down. It could be deuterium propellant, or you can mix it with hydrogen because it's cheaper and more abundant. We've done supercomputer simulations with the Los Alamos over the last 3 years to verify all this with 3D MHD codes. We have PIC codes in the work. And this is the first time you'll see, first time announced in the world actually, that we have these 4 jets merging and in a double helix fashion inside this magnetic nozzle and starting to compress. It shows that the whole thing is stable. You know, you never know when you do theoretical calculations and you go do 3D MHD simulations, whether it's going to be stable or not. So we're pretty satisfied that it is stable, and therefore our experiment should work. Now, of course, we have to do it for real. So in our labs today, we have built a machine. We have the first gun up and operational, and we're bringing up online the second gun this summer. And then by the end of the year, we'll get the 4 guns to be able to demonstrate the merging of 4 of these jets. The magnetic compressor is already being built and tested on the stand. We're just redesigning some of the support structure. And then later this summer, we'll bring it into the lab. This is in collaboration with the University of Maryland and with Caltech. The roadmap itself, the technical roadmap, is roughly where we're at now. We're what we call in our phase 1, where we're demonstrating all these 4 jets stable, merging together and being compressed by roughly a factor of 10. Then the next phase is to start reaching fusion temperatures, compress it to net gain, and then do a technology demonstration mission in a decade. Now, in parallel, we've already started doing planning on how to do flight tests of subcomponents. It could be the plasma gun, it could be the capacitor banks, it could be the control systems, all that, so that we'll be ready to be able to do the first, what we hope to be the first fusion propulsion demonstration mission at TRL-9. Now, this is a technical slide. It's really, many people ask me, how does this fusion drive compare to rocket propulsion in general? So it's always about thrust power and specific impulse on the x-axis and y-axis. Chemical, nuclear, thermal are very powerful on the top left, but because of the low specific impulse, they burn all their fuel out in a few minutes. Electric propulsion are very fuel efficient because they have high specific impulse, but they're limited by the onboard power. Magnetic fusion in general, I've shown in the dash gray boxes, are on the top right once they are steady state and operational and you have that reactant space that's flying. Our specific case is that we can scale down to sub-self-sustained fusion drives, where we are in what we call an electric propulsion afterburner mode, where we take the electricity on board and instead of just accelerating the plasma, we heat it up to fusion conditions with some net gain, a little bit of net gain, just so that you get more energy out than what you put in, and that allows you to push a spacecraft. And it bridges the gap, if you want, between today's world, where we have electric propulsion that flies, and the future world, where we want these fusion reactors to open up the solar system for us. Thank you.
Yeah, go ahead. Well, now you know a little bit about the Helicity as a company from Stefan, and you know a bit about the technology and the technology roadmap from what Seth just told you. And I want to talk about the third leg of this stool, and that are the applications. And if we can go back just to the title slide, because I'm just going to editorialize to begin. We are in the very earliest, most primitive stages of spaceflight, and we have lots of problems to overcome. We are, pardon the pun, light years away from that Star Trek future that we want. And 2 of the problems in spaceflight that I think everyone here is familiar with are, first, that launches are rare and dangerous and very expensive. They're so expensive, in fact, that very few applications are possible. Fortunately, the launch business is being revolutionized primarily by Elon Musk and SpaceX, who have invented a new technology. They've really made it practical to have a practical reusability so that they can launch much more often. They don't have to build a new rocket every time they want to recycle it. And because the capital cost of the equipment itself gets amortized over many flights, the price per kilogram to put things in orbit is dropping precipitously. And what SpaceX has done is so transform the market that none of their conventional competitors can keep up, except by now following into reusability. And we see that across the marketplace, and not just in the United States or even in the West, but even Chinese companies and Russian companies are now announced that they just have to. There's no way to stay in the old regime. Well, similarly, another big problem in spaceflight is that, unfortunately, the solar system is enormous. And it takes forever with our current technology to get anywhere. Missions to Mars take months to years. Missions to the outer solar system take years to decades. And forget about going to the stars with current day technology. It's too primitive. We can't build machines that will last long enough to make a snail's pace across interstellar space to the closest stars with our current technology. But what we hope to do with the development of the Helicity fusion drive is to change that game the same way that SpaceX changed the launch game. And if we're successful, it will open up applications that we can't even imagine today. I'm going to talk to you a little bit about some obvious applications. But just like the transformation in computing that went from rare to routine when we went from mainframes to PCs, and it gave birth to applications like the internet and social media that dominate the tech world today and make hundreds of billions of dollars in revenue, we expect that the development of reusable rockets and even lower price points with other technologies, coupled with really fast, efficient, affordable in-space propulsion that can take us across the solar system as much faster in the 2030s and 40s and 50s as we now travel across the Atlantic on a jetliner compared to the sailing ships that Columbus first crossed the Atlantic with. So that's what we're out to do. Now, in saying all of this, I'm painting a picture where we're going to invent and make practical a technology which we don't really understand what the real killer apps are probably going to be. The things I'm about to talk to you about are really obvious. They're obvious from our standpoint today. But when we really have this technology, I expect that this will look very quaint. It'll look as quaint as the time that I was once told by one of my elders when PCs were first coming online that she didn't think she really needed a computer in her house because she didn't do that much math. All right, so now let's take the first chart. So what are the applications? Well, I'm a science guy. And if we had fast transportation around the solar system, that would really revolutionize our ability to do things. You heard from Stephen that I've had the privilege of being the principal investigator, the leader of the New Horizons mission, which is now on its way to interstellar space, but at a snail's pace, despite being the fastest spacecraft ever launched. Our job was to reconnoiter the Pluto system and to go on and make the first reconnaissance of the Kuiper Belt. And we launched so fast that, unlike Apollo missions, when I was a boy, that launched at 25,000 miles an hour and took 3 days to reach the orbit of the moon, New Horizons crossed the orbit of the moon less than 9 hours after we left Florida. And yet it took a decade to cross the solar system, 9.5 years from Earth to Pluto, as the fastest spacecraft ever launched, and by a lot. What if we could do that in a year? What if we could do that at a year and at even lower price? We don't have that technology today, and we're not going to get it from any technology that we imagine. The solar sails might help in the inner solar system, but they can't buy us the whole solar system because the sunlight's too weak beyond the asteroid belt to make it practical. Gravity assists are great, but they only come when you have very special alignment geometries, and so you can't count on them on a regular schedule, right? And the rockets can take us faster and faster, but let's face it, coasting isn't the way to go. You need in-space propulsion. And we've started on that road as recently as the 1990s with the development of used to be called ion propulsion. We call it solar electric. Someday we'll have nuclear electric, but those are still systems that have low thrust, and modest ISP, much higher than chemical propulsion, but nothing like the system that Set's inventing. So with the development of a Helicity-like fusion drive, we can talk about traversing the solar system in very short periods of time, reaching the terrestrial planets in weeks, or even with very large, heavy spacecraft like spacecraft that will bring humans in a matter of months, and reaching the outer solar system in a year or even in months, and putting within our grasp doing things that today aren't really practical. Reaching the solar gravitational lens that we heard a lot about this morning, 550 AU. That will take New Horizons 2 centuries, at which point it will be long dead because it will run out of nuclear power to power the avionics and the communication systems, right? But with these systems, we can do the solar gravitational point in about as much time as it took New Horizons to simply reach Pluto. And there are other applications as well, if we can go to the next slide. But I want to stress that the systems that SET is developing can be launched by current day rockets, by Falcon Heavy, by Starship, by SLS. We don't need bigger launch vehicles. So we're not talking about putting a fusion, electric fusion power plant that weighs 10,000 or 100,000 tons. These are much smaller systems that can be launched once we develop them with existing rockets. Next slide. And that will then open up the solar system to all kinds of economic applications in addition to doing a lot more science. It will make the solar system our playground for humans and for robots, for economic gain, probably for social change, and for new knowledge. And it's going to be a completely transformational event if we can do this, and we are on the way to doing it at Helicity. I'm not going to quote any more numbers from this, but I just want to compare on the next slide what conventional systems take. NASA is working very hard to look at a possible interstellar probe mission, which would travel even faster than New Horizons and get out into the nearest reaches of interstellar space with much more speed and with much more payload than the Voyagers or New Horizons has carried. But that's still a mission that's set to last for many decades just to get to the nearest reaches of interstellar space. And NASA looks at other applications that also could involve better chemical propulsion or solar gravity assists, these O-berth maneuvers and things like that. And they all pale by comparison to the promise of what fusion can give us. Now, we're a bunch of steps away from having a fusion drive that can actually propel us around the solar system. We're starting in that laboratory in Pasadena, California. We hope that within less than 3 years, to have a first technology demonstration in low Earth orbit, not with an operational system, but just to prove for investors and for the community that funds this development that we're on the right path. And it's not just about doing it in a lab, but taking it to space. And then, as you heard from Stefan, over the next decade, to actually bring this to a practical flight demonstration of a real fusion propulsion system. Let's call it a Mark I. Forget the letters and acronyms that we use. Just call it a Mark I that actually can demonstrate that capability the same way that a decade ago, a lot of people thought it was funny when Elon and SpaceX kept crashing all those boosters that they couldn't quite get to land the first few tries, but then they changed the whole marketplace. So there are some other ideas for applications that are listed here. Cislunar space, we can transform it. Humans to Mars, forget about all those medical problems of zero-G because it doesn't take 18 months. What happens when it takes 18 days? Now, you don't have any of those problems of the radiation exposure. You don't have the problems of bone demineralization or any of the other concerns because we make the crossing so quickly that we change the game. We have very large systems in mind that ultimately may or may not be what we actually invent because there'll be other inventions that come along as we're inventing the basic propulsion that will let us further advance the field. Go ahead. I think the future is really unlimited if humankind can invent in-space propulsion that makes the entire solar system within reach, not of our most Herculean efforts to make spacecraft that last for decades and centuries, but instead to do what we did in going from the sailing ships to the steam-powered vehicles of the 19th century to propellers and then jet engines and soon hypersonics to take us across our own planet in shorter and shorter timescales that no one could have imagined in Columbus's time. And we are on the road to make that first set of inventions at Helicity that begin to open up that new future. And so that's the conclusion of our third presentation. Before we open it up to audience questions, we have a couple of questions that I wanted to make sure we got answered for you. And so let me start with this one. And it's a question for Stefan. How will Helicity monetize the fusion drive, and what's our path to revenue?
Thank you, Alan. That's a question we get a lot, as you can imagine. One way to answer this is to echo what Alan said. We don't know what the future holds with this technology. So we're still a little bit in uncharted territories. We know that if we have it, it's going to have many, many applications. The most immediate ones, the most concrete ones, will be most likely science missions for the smaller classes. If you can take a Mars rover twice the size to collect samples on Mars in a single mission, as opposed to the current Mars sample return mission that's 9 years with 3 flights, that has applications. And once we're at TRL9, for space agencies, for military contracts to survey things, there'll be government contracts to be gotten for sure. So that's one. And we're hoping to monetize that earlier on, not just once the drive flies, but secure funds early on. And we're working on a number of paths this way. Then there's the commercial angle. If we had this technology, a version of it, you can imagine Blue Origin, SpaceX, being very interested. And we've talked to the right people in some places already about licensing that technology as it matures. We still have a lot to prove. I mean, you've seen the lab. It's not exactly a flight demo yet. So commercialization is going to come through contracts. It's going to come through contracts from agencies as well, so public funds, as well as more mature space companies that will need the technology. The idea is to mature the technology with the commercial side in about a decade. I think that's usually our answer.
So the second question that I want to pose, and this one's for Set, is tell the audience what differentiates Helicity from other fusion propulsion companies and concepts.
So we're one of the rare companies that really focus on propulsion only. And before making power plants, most fusion companies really have thought first about how do you make electricity. And then sometimes they mention propulsion as an offhand. We've reversed the problem, and we sincerely believe that it's actually faster to develop a fusion propulsion system if you don't need to focus on making electricity 24/7. Just from a physics point of view, you need more energy out than what you put in. Just to be able to recirculate the energy to maintain that fusion reaction to go before you even sell electricity, you need gains of 25, 30, 40, 1 over the efficiency of just creating the fusion systems. But if you push a spacecraft, you don't make electricity, you can already do that with a gain of 4 or 5, or something like that. You can already start getting more power out than what you put in. So on the way to getting those large gains, you can already do something practical.
Yeah, very good. Last question is really for both of my colleagues here.
If you
want to add something?
I was just going to add one to Seth's comment. Just in case for this audience, when you're in space, you're in vacuum. And the problem with fusion on Earth is always vacuum. Here we have the most perfect vacuum chamber. So low gains in vacuum, pulse. The application is much easier, but the vacuum angle is one worth mentioning as well.
Right. So for both of you, and maybe we'll start with Seth on this one again, because it's a bit on the tech side, but how can the fusion drive that we're developing at Helicity more easily reach actual practical use than other concepts?
So it's mainly efficiency. We're trying to find the most efficient way of heating a plasma, and magnetic reconnection is the key. Literally, it's extremely efficient. It's about 90% efficient. Heats the ions directly and internal to the plasma. That's really the technical key. Not many other companies do that. And in fact, if there was a 1982 book on fusion research, and they were listing out all the different methods of how to do fusion. And they said there was only like 4 different types of heating methods. It was compression, plasma current, neutral beams, charged particle beams, and radio frequency heating. And then they kind of worked through all the pros and cons of each of these heating concepts. And then they said, if you could have an internal direct ion heating, that would be the best way of heating it. And that was before magnetic reconnection was harnessed in the laboratory. So that's one of the reasons why. And the fact that we're also doing magnetized target fusion and magnetized inertial fusion is we're doing things on an intermediate timescale, and it's pulse. You don't have to pulse for 1 hertz. You can do it less than a hertz. You can do it, and all the compression energy is going into the heating itself before you lose the heat. You don't have to do it in a steady state when most of the heat is lost and so on. So adding all those things means that the actual compression and heating system is more efficient.
Okay. Thank you very much. I think where are the students with the mics? Yeah, we're opening it up for questions. We have 12 or 15 minutes, so we have time for quite a number of questions. Gentleman in the front row.
Check.
Thank you. I have a bit of a naive question. So you prepare these Taylor states, and then with some distribution of magnetic fields, you can compress them. Is there a limit to how much you can compress it? Like, can I keep compressing it and gaining more?
Great question. Yes, there's always a limit to everything. The limit is what we call the beta ratio. It's a ratio of the plasma pressure, the thermal pressure, divided by the magnetic pressure that's holding it together. And that ratio in the lab, we've observed to be of the order of 0.5 to 1. We have quite large error bars. But that's probably what we expect to be the ultimate limit. So we start with a low beta, and then we have to compress it. The beta raises up to the beta limit. Yes.
Thank you.
As you know, one of the physical aspects of fusion that's been going on for, 70 years now, has been at the point of trying to get, you've got a staged system here where you actually reach the point of doing fusion. Have you looked into the problem of instabilities and nonlinear instabilities?
Yes, absolutely. So we've looked at a lot of different types of instabilities, and we're still in the middle of looking at it because instabilities is the bane of fusion confinement concepts. I mentioned the helical shear flows that allowed us to stabilize to the most dangerous, what we call the kink and sausage instability in these magnetic confined systems. That we've demonstrated was stable. The 3D MHD simulations allows us to investigate and extrapolate from what we see in the lab to see whether the next step will be stable or unstable. And at the moment, it's grossly stable, which is very welcome. Now, we need to validate all those theoretical and experimental results with the experimental results and continue scaling up that way. Yes.
Thank you for that question. Great question. Becky.
Yeah, Becky McCauley-Wrench, NASA headquarters. Very cool. I love this. I wanted to ask about, you kind of gave some numbers on like getting how fast you could get humans there and payloads and all of that. I'm curious about, for those numbers, what are the kind of stresses that the spacecraft or the humans might undergo? Like what sort of G's are they pulling as they get there that fast?
So the thrust to weight ratio is very low. Actually, let me go back to this picture here. You can see the thrust to weight ratio are these straight lines here. And to take off, you need thrust to weight ratios greater than 1, which chemical propulsion is still the best. That's what to allow us to take off. These ones are very low thrust to weight ratios. So they're actually just like winds blowing out the back of the rocket. So it's more the advantage of being very fuel efficient, and you can accelerate not in just 8 minutes, but you accelerate over maybe a month, and the final speed is larger.
Perfect. Great answer. Thanks.
Maybe to give you another number that's interesting is the time it would take to get to the moon, because that's not 3 days. It's more like 20, 50 days, because it's not one boost. It's like you said, it's a sail, so it will take time. So for the moon, ironically, you won't use, when we say cislunar, you won't use these drives to bring humans to the moon. That you use chemical reaction and get people there in 3 days. But for heavy cargo, where you need very little fuel, that's what's helpful in cislunar. So it gives you a sense of the speed.
Hi, Garrett Bruhog from the University of Rochester. So I have tons of fusion questions I'll pick your brain about later that would bore everyone. But I specifically wanted to ask about the intermediate stage you were getting at, assuming you can get this wonderful machine working and you want to start doing these low gain propulsion missions with solar electric driving it. what sort of advantage does that really provide when about half of your energy is coming out as neutrons that you have to shield against, and a normal solar electric system wouldn't have that problem?
So we're planning to use DD. So DD fusion for certain reasons, because it reduces the neutron flux. It's only about 30%, 32% in neutrons. So you have 60%, 68% in charged particles for the thrust. So the neutrons you just vent out to space. That's the plan. To make it as light as possible with minimal amounts of shielding. Now, ultimately, for any kind of mission, it's a thrust to weight ratio. So we have to inventorize the mass, the total mass of the engine, which is, we've done a crude inventory of what the weight would be. And the curves that I showed was to show that at the small engines, the thrust to weight ratio is comparable to nuclear electric or solar electric propulsion at that kind of class. But then it has the potential to scale up, because you can increase the numerator, the fusion thrust power, and then keeping the denominator reasonably intact. So then you can really scale up. While with fission electric propulsion, for example, you will always be limited by the worst culprit, which is the mass of the fission reactor itself. So at least this allows us to scale beyond.
On that slightly, radiation shielding has a set limit, no matter what your power is, at least to start. So it seems to me that at those low powers, you would still be in a pretty rough position, and you would risk damage to other spacecraft.
Neutron shielding protection is going to be a prime requirement, and it's going to be at the back with a huge truss, to the payload for sure, and you're going to put some shadow shielding for sure. But when you inventorize all the mass, that's a feasible path.
I'll just add, if you notice the artist concepts, that it's not all about shielding, it's also about the distance. That's why those spacecraft are very long, right? You win like R squared.
Thanks. I'll catch up with you later tonight and ask plasma questions.
Hello. So if I understand correctly, your drive doesn't generate any electrical power. So where's the power coming from to generate the plasma, and is that taken into account in your calculations?
So yes, at the small scale, it doesn't generate electrical power. So the smallest one, the simplest one, is the afterburner, and you take solar power, or you take, so it has the same limitations. But as you grow bigger and bigger, you get more fusion, you will absorb some of the neutrons, or if it's helium-3, you don't have as much. You Bremsstrahlung radiation conversion, synchrotron, and so on. You use some of the heat to do, generate electricity on board, but it's not sufficient to be self-sustaining yet. So it just augments what's coming in from the solar panels. That allows you to really start going up in terms of the output, until eventually you make it so big, you're back in the usual reactor mode where it's fully self-sustaining and you do have a power plant. It's still smaller because it's magnetized inertial fusion compared to magnetic fusion. So there's at least that path of being able to go to self-sustained mode.
And did you take the mass of that system in the self-sustaining mode into account?
Yes, we take the whole mass of everything into account. Yeah, radiators, everything, shielding, everything.
You can see the pictures, Eric.
In the middle, you see the non-self-sustained, the smaller versions, and then you'll have the one on the right for 2040s has the shielding around that will recirculate, capture the neutrons, etc. It's a rendering, but gives you an idea.
And we're very particular about counting the masses of every system, because the denominator plays a very strong role in a specific power. I noticed.
So hopefully this is a softball question, and it has nothing to do with fusion. But a big component of your mission plan is reusability. So how are you addressing the erosion of the components? Is that a significant problem that you're facing, or is that something that you've already got the solution in hand for?
So I'll give a chicken answer, because we'll kick that ball down the road, but we have thought a little bit about it. One thing is we have multiple guns. That's unique to our concept. The plasma sword, you can think of it as, some people might be familiar with a Z-pinch, for example. That's just one plasma gun making this jet coming out the back. It could do fusion if you increase the current. But if that plasma gun dies, that's it, you're done. In this situation, we can have, say, 20 guns. You're distributing the same amount of input energy over 20 guns. And then each gun, for example, if you have one that dies, you still have 19 to operate and so on. Then you can start doing advanced scenarios. If you want to refurbish the gun, you can pull it back in, replace it with a new gun during its pulsing of, once every few minutes, for example, or a few seconds. Things like that. You can do all these kind of games, to try and minimize erosion, for example. Yes. So then there are ideas about the advantage of space as well is you don't have to absorb all the neutrons, all the radiation. You can try and vent as much as possible out to space. So we have ideas on how to do that from an engineering point of view. Yes.
Okay. So in the presentation, there was one of the future steps, I think, would be injection into the nozzle to get perhaps higher RSP. You were thinking of adding mass. Have you done any modeling of that? And do you have a good idea of how well you'll be able to mix what you're adding into your fusion stream? Or is it, because it's an old concern that the mix might not be very good and you might just be dumping fuel right beside your fusion reaction?
Yeah, the efficiency of thrust conversion from the charged particle right now, we've got some experimental work from past work where we shoot a plasma jet into neutral gas of different shapes and different sizes and different configurations and see the interaction between the plasma and the gas itself. So yes, we have started looking at that, but let's get steps 1, 2, and 3 nicely working. And we'll get to 4, yes, promise.
We're
Okay. My question is about monetization. So I'm really curious about how far you can get with just commercial private sector investment. And when is it going to become crucial to have government investment come in? And I say this because I spend my day job is to go walking through NASA headquarters trying to convince powers that be to invest in things like this. And it's very difficult until it hits sort of like a tipping point, right? Situation where people believe in it. I think there's 2 things to that. One is a proof of concept, and it's hard for us to get the real money you need to do that until you show it. And so it's kind of a chicken egg thing. The second part of that is, what are you selling that's got a real connection benefit to what we need now? And I think the Alan mentioned it was fast trips to Mars. It is just coming up again and again. They're desperate to find solutions for that. So those are the two things I think you have to address, but I'm wondering how far can you get before it becomes so crucial that you get investment from folks like us?
So the earlier the better, obviously. And then there's a question of what investors want to see. At this point, what everybody wants to see is what you see on the top right here. That's what's being built right now. 4 jets reconnecting, compressing. So the compression will be demonstrated this year. That was your question. It's not deep in the future. This year, at low energy, we're getting 4 jets to reconnect, compress. That's never been really done before. There's the simulations. We know that 2 jets heads on also merge, but this is really the proof of concept. It's a $5 million investment overall. The private market has funded it. DOE has governance money already in small grants. That has helped. And what the investors want to see is a roadmap that's reasonable. Like, what do you need for phase 1? What do you need for phase 2, phase 3, phase 4? The numbers each time increase when you go to space flight at some point. These start to be sizable numbers. What the private market loves to see is commensurate commitments from NASA or others that show that there's interest. At this point, we don't need large amounts, but small tokens really show that NASA is interested, believes that this technology may work. All our advisors, the key word we like to talk about is we don't know if this is going to work. We have reasonable belief that it has good chances of working. And that, for this type of technology at this stage, is the best we could guarantee, unfortunately. So commensurate help that shows interest, whatever discretionary is, would make sense at this stage. When you get to phase 3 and you've got already neutron demonstrated, you're getting close to net gains. Well, that's when the private markets will pour a lot more into it, as they've done for other on-Earth fusion. And that's where we also expect DoD and NASA and others to step in, because we're much closer to flight and commercial applications. We'll know a lot better what the actual sizes are, what the actual masses is. Everything we presented today is our best guess. After 4 years of heavy work, these are not, set to make up all these numbers out of thin air. It's serious work behind this with a number of advisors, but So commensurate in locksteps is the ideal setup.